question is the research. Okay, let me see. Okay, here on the recording. So the research question is about describing the foundation of today's generative AI, the foundation model, which is predict the next word or token or state of the word in terms of where things are heading there, with the simplest possible logic formalism, so that inference steps constructively model the key element in the foundation of generative AI that made it all happen, in fact, which is the next token prediction. Of course, that's based on statistical data on that side, but the underlying logic is shared, and that would be the main uh, point of what's coming next. So, what we want then is this minimal system that explain LLM style prediction. And for that, I will only use something that's in fact uh, it's all present already in Hornclose logic, which has an intuitionistic reading. I think Dale Miller's book is all about that, how you can interpret the semantics as well. So all I have is implicational intuitionistic logic that also via Curry Howard corresponds to type theory, and it can even correspond to Herbrand terms if someone wants other syntactic variants of the same. So we would encode prompts as implication chains, and the way we parenthesize would capture order. Now, it is known that for large language models and transformers, they need a separate layer to encode positional dependencies. And here we will see that we can actually do both of them by having this ordered representation of um, implicational logic. And let me move to the next one. I think that should work. So we have left-leaning and right-leaning nested implication chains. Uh, if you look at that sequence of words here, W1, W2, and so on, and the little implication symbols, you would see that, like in Prolog, in fact, implication is right associative, right? So by default, unless you put parentheses, it would read like on the right side here, the RN. Uh, Now, what's very different between the left side, ln here, and Rn, is that the right side is equivalent to a conjunction implying the last element. So, of course, conjunction is commutative, and here we get basically the whole clause, the original, SLD resolution, whole clause semantics in which the order in which you expand the goals to prove the head of a clause, right, is arbitrary. Now, if you have this model here with left nested implications, that's almost like continuation-based binarization in which you force a given order. So we will rely on this form here to um, show some of the um properties that are different in the two cases. I have in the paper and also the website, the GitHub site contains a complete code of everything I'm talking about. There is a theorem prover for this subset of implicational logic. And when we look at the little relation here, P implies Q implies R implies here Q implies P implies R. If you commute the elements inside here in the nested implication, that would not hold. On the other hand, here you can commute them for free because that part here is basically a conjunction, and then P implies Q and Q implies P here. They both become Q and P implies R, and P and Q imply R. So what we have here is then a function type that changes when order changes. And here what we have is the antecedent behaves like a commutative bundle of assumptions, conjunction like. And the concrete example here is that we have actually a very simple inference form here. We don't really need a theorem prover for that. All we need is modus ponens. And assuming here that we have a full chain uh, that is of this form here. The final chain is an intermediate chain implying W. Then predicting W is just applying, assuming that this is already digested, and then this implication holds here. From those two, W uh, comes out as just applying repeatedly modus ponens. So that's a very simple logic behind the next word prediction mechanism. So in practice, when you have a sentence here, a very little toy one, the cat sits, and the same thing is replayed here. The cat sits, the cat, and then the cat is there. Then from those two, you can infer that sits is provable in this very, very weak logic. And of course, the theorem prover also creates the lambda terms, which are the proofs, actually, if we want to see the proofs. Now, the next, uh, there are a few theorems that hang there in the paper that this also can explain multi-token prediction, and it can be actually used to make a system that can do information retrieval at relatively large scale. Um, what I modeled here is two different things. One of them is all in Prolog, and it digests War and Peace and a very large the Germant and a very large Gutenberg available public domain stories. And you can do information retrieval on that in less than a second in Prolog with this implicational formalism. And the code is on GitHub for that. But the second part, which actually brings us to the derived from this purely logic formalism uh, Arrow language model, this time is a Python code that actually implements a form of recursive LLM. It's not like transformers. It's basically each token is an operator that updates the state of the proof or the equivalent of the state of the proof. And because we have matrix operations that are uh, non-commutative here, we get exactly the same asymmetry as with the left-nested implications. So the result of that is that we actually derive, I am skipping the very low-level Python parts, but the link at the end of the slides, the code is completely there and it's runnable very easily, even on a small machine. It's a very efficient implementation overall. Uses the torch, and if there is a GPU, it uses the GPU and so on. So this arrow model basically, interestingly enough, uh, turns out to be a rediscovery of one of the seminal paper by Sutskever and Hinton from 2011, where before transformers became popular, they tried to um, model recursion in a different way. So it's a form of recursive language model that was reasonably successful before the big transformer wave came out and well replaced everything else. So here's the final slide. That's the related GitHub repository. It's called Next Word, and they include the Prolog code that I mentioned, um, as well as the related Python code. So thank you very much for listening to me. I hope I was reasonably time efficient. And
Very well.
if
And
you have
pretty.
questions, please go ahead.
Any questions? Jason. Oh no, these are comments. Who'd like to ask any questions?
Okay, stop the sharing. Um,
So, Paul, to place it, basically, you would use this logic-based approach to generate the next token, essentially. And so, would it work very much like an LLM? Is that the idea? But the engine is logic-based.
Yes, yes. So I have two models that are doing exactly the same task. One is purely logic-based, is Prolog with this implicational theorem prover attached if needed. And on the other hand is the LLM implementation in Python using Torch, and they work on the same data sets and produce the same results. And they're very efficient. Prolog is actually still faster a bit than the corresponding Python implementation that needed to do some heavier machine learning and requires GPU and other resources. Prolog queries War and Peace in less than a second on any question that you want to send. So that's out there, and it's testable basically.
Right, right. So basically, you right? It works on input like the Gutenberg Bible and things like that. You said, right?
Yeah, and
So
Moby Dick and all the big
I see. So if I ask questions, it will very much work like an LLM.
the Prolog
Or
part emulates
I
LLMs.
see.
Now, of course, what it doesn't do, and this is the main limitation, is that it didn't digest the whole universe uh, to know about everything else. It's trained on a specific document, like a proof of concept, basically. It is not a real LLM competitor that takes
Ah,
over the
okay, okay.
wars and you know turns logic programming into the next big AI. It's a proof of concept that the logic structure is very similar, and then interesting things that happen on the Gen AI side can be modeled in logic and explained, especially explained possibly to people who want to learn about what's going on foundationally inside the LLMs.
So if I ask a simple question, about the Gutenberg Bible, essentially we will get an answer that is somewhat, I mean, may not be exact, but at least, the right words will be generated or the right
Oh,
sentences in the
yeah, yeah, no,
ballpark.
it's not just the Gutenberg Bible. There is this Gutenberg.org
Okay, the whole.
collection that contains all the publicly available copyright free documents. Mm, all the major writings that are
Oh, I see.
century
So it's
more
not
or
just
less.
the Gutenberg, but all the documents from on that website, on that site.
Yeah, you digest a document at a time, and then you can start the querying either in Prolog or via the LLM in Python.
So then in theory, if we were to we could implement basically a Prolog based LLM, and then ideas that we will get the same result. But
At a small scale, on that specific content. That's the limitation because the real LLM is the internet that you need to
But we could
feed.
scale it up, right? I mean, if we had the resources, we could do the same thing.
Yes, yes, it
Right,
can be
right.
scaled
And then,
up. The model is not as strong as transformers
okay,
because it's the equivalent of the Hinton 2011 model before transformers, but it's a very simple and there's some very nice algebraic things about matrix operations. Lower triangular matrices that compose and that's a completely different story there, but the uh, the code, the Python code that's related, it's relatively small actually, and maybe 500 lines or something like that
I
in
see. And then I
Torch.
could see the token chain or the word chain and basically sort of figure out why this answer was produced, right? I guess that's right. That's one of the ideas behind doing this.
Yes, yes, yes. It's a kind of an explanation mechanism based on logic more than anything else.
Okay, all right, yeah, that's
And if it could
super.
be combined with reliable knowledge bases, it would even go a step further than current LLMs. And to tie with the initial comments, without getting into AGI, which of course is not here by any stretch of the imagination, but do you think we could combine it in order to even go beyond what LLMs are capable of in terms of trustworthiness?
I think the future is bringing in uh, validation of the uh, LLM output that's based on independent reasoning. The trend is very strong out there because they are not hitting necessarily scaling limits on the actual intelligence of they solve Olympiad problems and so on, but they are hitting truthfulness limitations and trust. So now the big challenge is uh, to bring in trust, and that applies not just to natural language, it applies more and more to coding. There are a lot of coding assistants from either Anthropic or OpenAI, among others. And the code that is generated now, it's called vibe coding. Basically, you do not type on the keyboard anymore. You just try to be very clear about what you want and then make it do it for you with the problem of the truthfulness. Are you sure that what comes out is what you actually want? So that part could be validated by a logic, a knowledge-based skeleton that represents your code base and your applications basically. So there is a lot of room for logic programming to come back and take over those niches that are not covered.
So Paul, to continue, I mean, to just trying to understand. So basically, if I have, say, the cat sits and the cat jumps. So now if you go from the cat, I mean, again, from what I got, the way, you had the implications. Now after the cat, you have, right, you have a choice to make. So how are those type of things resolved?
So if there are multiple answers in Prolog that is non-deterministic, they would come out all. If there are multiple continuations for something, but that happens with LLMs as well. They are just a probability curve with softmax. Basically, you get 100 candidates with different probabilities distributed, and then you depending on the temperature, when you use the query, you can say, okay, give me the most likely. And
Right, right. So the
you
LLM would basically make a choice, based on the probability values. But what would you do in Prolog? I mean, you would actually do non-deterministic, follow it and then backtrack and try something else, or because that's basically what LLMs do, right? That they build these giant probability distribution table, and at any step you have a choice, you choose the most likely one. So it's basically the way I view it, it's example-driven search, that you look at the examples that you have, and these examples are guiding your, selection of the next token or next goal or whatever, right? So how do you incorporate that in some way in your Prolog implementation, or how does that
So
give it
what
its back?
happens is that once you commit to the next word, right? Like in this case, the cat, let's say, sits.
Right.
Once you commit to sits, then well, on the mat will become more likely than it was before. And otherwise, as a small proof of concept for the information retrieval part, that it will give you all the answers. Actually, you want to retrieve all the sentences that match that particular query for this. And I have a sentence splitter. So the documents are read, Gutenberg is cleaned, and then there is a split into sentences, and those sentences become then the basic unit on which everything works.
What is that noise from?
It didn't happen for, I don't have an iPhone. It was just an iPhone that connected, maybe.
All right, let's continue.
Yeah. Okay. Yes. Thank you, Paul. Yes. Yeah. Try it out.
Well, thank you for your attention, and we can get back to the usual meeting. I will be listening. I'm not showing my face because it's not the best thing I can show at this time, but I
Your
will be
voice is
here.
already a precious gift, Paul, always kind and tranquil, as usual. And we are
then
very, very
congratulations.
grateful that you have been able to join us today and give us this wonderful talk that we'll for sure continue working on, because I think we could eventually join it with reliable knowledge bases and get somewhere beyond what LLMs do, even if we use the usual LLMs, but at least we have the logical justification. I think that's a fantastic contribution you've added to the already enormous pile of fantastic contributions you've done to our community. We thank you from all our hearts.
Thank you for
Thank you
indicating to
all.
us this fascinating line of work that we will certainly continue. Thank you.
Yeah.
Thank
Any
you.
other comments before we go? Okay.
Yeah.
Thanks.
Thank you.
Thanks a million. Bye.
Yeah.
Thanks.
Yeah. Thank you, Paul, for
All the best.
Thanks.
all your wonderful contribution, and we wish you the best.
Thank you.
Okay.
So I will stop recording. Sorry.
Oh, yes.
Yes. Okay.